Yes, I can.
So let's look at this problem where the covariance matrix is, or a function is given to be a two-variable function, t1 comma t2, and so question is this an autocorrelation function? So what we need to do is create a matrix out of this. So this will be whose ijth entry is, so this is Rij. Rij is minimum of ti comma tj. So first row and first column, first row will be minimum of t1 comma t2. So let's say t1 is t1 t2 are in this order. T1 is less than t2 etc. tn. So we picked up points. Remember we have n points. Call them t1 through tn, or the arranged one. So the minimum of t1 t2 etc. will be t1, the first row. Similarly, the first column will be T1. Do you see this? Hello, everyone, do you see this or no?
Yes, sir.
So what will be the second row and second column? Anybody? Starting with, huh? What will be the number here at the 2, 2 position?
T2.
And this will be T2, etc. So this is the key observation. You need to make sure that this will be T2. Agreed? So what will be the next row and column?
T3.
Very good. So this will be T3, T3, etc. T3, and here also T3, and the last one will be Tn, right? So I'm going to write this as the sum of two matrices. Then you will see what is going on. So I'm going to take the first matrix. So you have to, only at the end you will see what I'm trying to do. So let me pull out the T1 from everywhere. So this is a matrix with all T1s. So what will be, to compensate for will be, what will be this matrix? Anybody? Tell me quickly, what will be this matrix? First row. Because this plus this should give you this. So first row will be what?
0.
How about first column?
0.
And how about second row? Second column. Remember, I pulled out T1, so each entry will be subtracted by
T2 minus T1.
Yeah, so this will be T2 minus T1. Next entry will be T2 minus T1, etc. T2 minus T1. Similarly, the columns T2 minus T1. And T2 minus T1 is positive because, look at here, T2 minus T1 is positive entry. And the next entry will be T3 minus T1, etc. Last entry will be Tn minus T1. So that's fine. But look at here. Let me concentrate on this matrix. This matrix can be written as, this is the whole key. See, a vector, I'm going to call this E1, and it's a transpose. Because you pull out T1, then it will be all ones. So you get, this will be, and this is E1 transpose. And so you continue the same thing here. You pull out the T2 minus T1 outside. Then this will be from everywhere. So this will be 0, 0, 0. What I mean to say is, so let me go to the next page. In this matrix, you write it as T2 minus T1 everywhere, same entry. Plus another matrix. So I'm going to go to the next page. So capital R, we saw that we can write this T1 multiplied by E1, E1 transpose. Then I have T2 minus T1. If I pull outside, that matrix will look like this. All zeros before, all zeros. Then this will be all 1. And then there is a third matrix which will be all zeros first row, all zeros second row, because I pulled out T2 minus T1. Anybody can tell me what will be the third row? Because from every entry you have to, I have pulled out the T2 minus T1. So from T3 minus T1, if I subtract T2 minus T1, what do I get? Anybody?
T3 minus T2.
Yeah, that's the whole point. This will be T3 minus T2, etc. Last one will be Tn minus T2. But look at here. This also can be written as some E2, E2 transpose, where E2 will be 0, 1, 1, 1, etc. E1 was 1, 1, 1. So if you continue this, again you do the same thing, pull out the T3 minus T2 outside. So if you continue this, you can write this as E1 E1 transpose plus T2 minus T1 multiplied by E2 E2 transpose plus T3 minus T1 multiplied by E3 E3 transpose. E3 will be, you can see the same pattern, 0 0 1 1 1 1 1 etc. This was 0 1 0 1 1 1. This was all ones. And plus etc. The last entry will be Tn minus 1 multiplied by En transpose. En will be all zeros except 1 at the bottom. So this is a manipulation you have to do. I hope you have seen this. I'm just going over it quickly. Then the whole point is, if you take any arbitrary vector and multiply that with the left and right so that this becomes a scalar, then you see I can do it on each one of them. So this I can, let me write this up. So this will be, I can write this as Ti minus 1. I goes from 1 through n. And with the Ti with the condition that T minus 1 is 0, then this is simply AI, A transpose EI, EI transpose AI, A transpose. But A transpose EI, conjugate is the same as, everything is real here, so just transpose. Let me call A transpose EI to be some new vector, let's say BI. Then in the next page, I have shown that A transpose RA is summation Ti minus 1 or multiplied by, so if this is Bi, that's the key, this will be Bi as transpose. But Bi is A transpose is like this. E transpose EA is like this. So A transpose EA, this is a scalar. So BI transpose is just the absolute value squared. So this is just BI squared. Notice this is positive. This is positive, so everything is positive. That's this is what a proof is. So see, these things you cannot do this unless you see things like this. These are ideas and techniques. So you should try to. This is why you need to sort of see few things. Then you can follow similar stuff. So use the same argument to show that if I define Ri, Rti, Tj to be, I'm going to leave it to, actually there is a, if you take this function, you can show that this is non-negative definite, but let me leave it to you to, because there are, even all these are solved in my videos there, or for example, Ti plus Tj. But Ti plus Tj is not a, this is not an autocorrelation function, but if you flip, if you invert it, this is an autocorrelation function. Why? Again, so few, they are not obvious to you, need to me, but if you, for this function, you can show that actually if you create a matrix using these entries, that matrix is positive definite. So remember, all I want to mention is a matrix is positive definite. If you take any arbitrary vector and multiply this way, this may be transpose if it is real or complex. This should turn out to be a non-negative number. So that's what you need to show. So what I'm asking is, if you have an R, I don't know whether you have seen my proof. If you have an R with Rij equal to this, I want you to show that this matrix is positive. Now, if you keep asking me how you do it, I'm saying watch the video and then see, and then you should be able to show that even if I square it, that's a positive definite matrix. So remember, necessity is the mother of invention. So right now you have a need to learn about positive definite matrices because they are all autocorrelation functions. So you try to learn all the properties, then you can use them. So let me leave you with another thing I want you to ask. Suppose R1 is a positive definite matrix. R2 is a positive definite matrix. Do you know how to multiply two matrices? Anybody? Let's go.
Yeah,
Ufek,
here I am.
do you know how to multiply two matrices?
Yes, sir.
All right. So I'm going to do a different multiplication. This means you create a matrix whose ijth element is the ijth element of R1 multiplied by the ijth element of R2. Anybody knows what type of matrix multiplication is this? In other words, what I'm trying to say is, if A is a matrix with the entries Aij and B is a matrix with entries Bij, I'm going to create a new matrix Cij, where Cij equals Aij multiplied by Bij. This is not the way you multiply matrices. This is the way children will multiply. If you give them two matrices, they will multiply. This is called element-wise multiplication. So what I'm going to ask you to prove is, or simply look at different books, etc. So you write it this way. This is a special symbol. This is called the Schur product. So here is the theorem. If A is positive definite, B is positive definite, I want you to show that C is positive definite. So that means if I multiply take the Schur product of two autocorrelation matrices, I get another autocorrelation matrix. This is what you need to show. This is not the regular product, this is Schur product. Ufek, did you understand what I said?
Sure, thank you.
Have you seen this result before?
Yeah, actually, it was in the homework. We went through the videos.
Yeah, right. Did you do it?
Yeah.
How did you do it?
Well, I mean, I went through the video. There were some points that I didn't totally understand, but
why don't you, maybe for some of your friends who hasn't seen, these are my videos, you mean?
yes, I can actually ask a question here about the R matrix. So what I was confused was that we were always looking at these random processes such as x of t. And here we have the R as a matrix for the first time. And that was a little confusing for me.
All right, so remember.
Here an infinite dimensional matrix, or is it a discrete random process we're talking about?
No. So it doesn't matter. So let's say this is a stochastic process, right? Yes?
Yes.
This is a stochastic process, continuous time, right?
Sure.
And I can create an autocorrelation matrix in two continuous variables like this.
Sure.
Yes?
Sure.
What the property we are saying to say is that if I take arbitrary time instance t1 through tn, I just take n time points, right?
Mm-hmm.
Remember, where I leave everything arbitrary. Tn1, Tn, T1, T2 are arbitrary. Then I can, if I put that, if I call R Ti Tj, Ti Tj as Rij, then I can create an n by n matrix, right?
Oh, so that will be.
No, hold on. Let me finish this. It will be an n by n matrix, right?
Yes.
So what we have shown is, if you look back, if you take a continuous time process and you pick up any time instance T1, T2, Tn, and you create any n by n matrix, it doesn't matter what the size of n is. N can go all the way to infinity. For any value of n, this matrix will be positive definite. That's what I have shown.
I see. I totally understand.
All right, so the conversely it goes. It doesn't matter what value of n, it will be always a positive definite matrix, whether the process is discrete or continuous.
Sure.
All right, so how did we prove it quickly? If I call this matrix to be R, I look at A transpose RA. And if you recall, the proof was very simple. This is expected value of xt1, xt2. X is a vector now because vector of all this, and multiplied by A. So take A inside, so this becomes expected value of A star x of t. That's a scalar, so it's absolute value squared, so that's positive. So the proof is very simple. But now you can use all the, if you know the positive definite matrix properties, then you can bring it into this course. That's my whole point.
Sure,
Of
thank
course,
you.
if you know nothing about positive definite matrix, then you are at a big disadvantage. So please start reading up. I also sent you a video on by me on positive definite matrices. But you should start reading books. There are hundreds of books on linear elementary matrix algebra. So it will be useful. So as I said, this is a standard result. If you take two non-negative definite matrices, then it's a sure product also is non-negative definite. And yeah, I mean, many ways you can prove this. If you know the eigenvalues and eigenvectors, that's an easy proof. So for example, if A can be written as lambda I ui transpose. This is the eigenvalue representation, where all the, if A is non-negative definite, then all the eigenvalues are non-negative definite. And the ui's are vectors. Now, if you ask me why is this true, then you have to look into singular value decomposition, etc. And in fact, the video I forwarded goes through all this. And if B is also non-negative definite, then B also can be written like this. Notice there, so this will be some Vj transpose. Vj is like this. So remember, B is a matrix, A is a matrix. Now I am going to take A should be, so I'm going to do the proof quickly. So you can do the Schur product on these two. Remember, Schur product of two scalars is just ordinary multiplication. Then you have to do ui star, Schur product Vj star. This is a scalar, this is a, I mean, this is a vector, this is another vector. But remember, these are rank 1 matrices because here the main entry is, what is it? Uij star, right? That's the ijth entry here. The first I standing for this I. And here similarly, this will be Vji Vjj star. When you do the Schur multiplication, you are just, because this is just a matrix, so this is this multiplied by this. I'm going, you have to obviously follow this. So this will be something like, the entry will be here, uii, uij, vji, vjj. But you see, I can group these two together, I can group these two together. So this becomes, so the bottom line is I can write this as in this form, where this is uii, this is vji, this is, so this is a new vector, this will be uij, vjj. So this will be a new vector, this will be a new vector. Call this Ci if you want. So this will be Ci transpose. So what we have shown is, remember there is two summations, lambda I mu j, two summations, lambda I mu j. So what I have shown is this A should B can be written as lambda I mu j, both are positive, then some vector which is like this, multiplied by its transpose. So this is positive definite because that's the any positive definite matrix can be written like this. So I showed you that this funny product also can be written like this. So this is a famous theorem. The Schur product of two non-negative definite matrices is non-negative definite. So the Schur product of two autocorrelation matrices is an autocorrelation matrix. Simply it means that if you take element-wise product of two autocorrelation matrices, that will be an autocorrelation function. So you can use the same argument to show that RTI, Tj, T1, T2 is an autocorrelation matrix. Anybody? How will you prove that this is an autocorrelation this is an autocorrelation function? Ufek, do you see it? How to prove this?
Not super fastly. I should think about it a little.
What is there to think? Look at what is the what is the ijth element? Anybody? Tij, right? Yes?
Yes.
Yeah, so I have a matrix whose ijth element is Tij. Do you see, you can write it like this because this is simply T1 through. See, this you only get this by doing problems. See, I have been able to write this autocorrelation matrix or as a product of the same vector and its transpose. So this is AA transpose. But anytime I can write it as AA transpose, it is positive definite. Do you see it?
Yes, now I see it. Thank you.
All right, so what about this function? T1, T2 multiplied by minimum of T1, T2. Is this an autocorrelation function? Anybody? I am asking you, is this an autocorrelation function? Yes or no? Anyone in class?
Yes.
Why?
Yes.
Why is this an autocorrelation function?
So, Professor, just before you you have given the proof of Cij equals to Aij into Bij, where Aij was positive definite and Bij was positive definite. So Cij is basically saying T1, T2 is positive definite multiplied by minimum of T1, T2, which is positive definite. Hence, it is a positive definite.
Yeah, a positive definite may not be the right word. Non-negative definite. At least we know it's non-negative definite, right?
Yeah.
All right, what if I square this function here? Anybody? Is this an autocorrelation function? So it goes back to this. So T1, T2, is it an autocorrelation function? Hello? T1, T2. Are you going to respond or you're going to just sit there? Anyone?
Yes.
So what if I square it?
It is an autocorrelation function.
Why?
Again, you can write T1 multiplied by
All
T1
right.
into
Very good.
T2
So I
into.
hope you heard his argument. So if you square a autocorrelation function, you will get another autocorrelation function. Remember, that proof comes from the Schur theorem. So you should go home and see how I proved it and make sure you understand the proof. And this is how you move on. Everything you don't have to, a lot of things you have to deduce. So all these are autocorrelation functions. But if I remove this square here, if I remove the square on this, that's not, this is an autocorrelation function. How about this one? T1 squared, T2 squared. Anybody? So this is not an autocorrelation function, but it takes some doing to see that. So anyway, that was, I think, the homework and this and that maybe. So let me get on with the main topic. Anybody has any other questions? We can discuss it.
Yes. Professor, for the winner process with Gaussian increments. So I searched from the Wikipedia, like for each increment, the variance of the increment is u, but in our homework, and we have a coefficient before coefficient like in our cases, our step has a normal distribution of zero mean and alpha u. So is there any differences that
No. I remember, take alpha to be 1, that's all. Alpha is just a constant, it's not going to, just a scaling function. So if you put alpha equal to 1, it becomes same as what you have seen, right?
Okay.
Yeah, remember, so the variance is what? T2 minus T1, right?
Yes.
Multiplied by alpha in our case, right?
Mm-hmm.
Yeah.
Yes.
Yeah, so it's exactly the same, just a little more general, but nothing much. All the properties are the same. Any other questions? So this is a problem I like to ask you. X of t is, yeah, as you said, a Wiener process. Take this down, this problem, and see whether you can find out. So cosine of x of t plus theta. The question is find the autocorrelation. What is RYY at T1 comma T2? So please take down this answer. This will tell you, give you an idea where you stand. And please don't try to solve these problems by yourself. So I hope you see the problem. The cosine of x of t plus theta, where theta is a random variable independent of x of t. So essentially, it's like when you transmit a FM waveform or a PM, phase modulation, and theta, the phase gets disturbed by a random variable theta. Question is, what is y of t the new process, Whiteson stationary or not? So you need to find out its autocorrelation function. So I'm going to leave it to you. Again, the solutions are there somewhere. But this will sort of tell you where you are, whether you are able to do these kind of problems. But we can discuss this next week also if you are not able to do it. But copying things from somebody is not the answer. I just want you to learn. Any other questions? Otherwise, let me go to this topic, new topic. Hello? Anyone? Sakshi Mishra? Sakshi,
Yes, sir.
do you have any questions?
Not for now, sir.
Kublai, Ulgar?
Yes, I don't have any questions either.
Did you understand what I said earlier about the Schur function?
Yes, I did.
Did you know it before?
Sorry? I
Did you
learned it
know
while
about the
doing the
Schur-
homework. I watched your videos.
Okay, very good. So let me go to the new topic. This is we are mainly this is where the applications start. Usually we have a receiver. It's some function, and you apply a stochastic process usually to with some purpose in mind, and you get some output signal. So the question now, what we are going to see is the input-output properties. So we can assume that we have a autocorrelation function here, and we want to find out the autocorrelation function at the output, etc. So it's pretty clear if you apply a stochastic process through a system, you'll get a something output. And if this is, if this is various realizations, there will be various realizations. So it's pretty clear stochastic process will generate another stochastic process. Now the function can be nonlinear or linear. Mostly we are going to study linear systems. But I'm going to just sort of nonlinear. An example is but nonlinear but memoryless. You can have memory also, but let's say this is so that means y of t is simply like this. It only depends on the current type, something of this sort. So could be x of t cubed, etc. Okay, that's a memoryless system. Now, in my lecture notes, I have derived the cross-correlation function for input and output. Remember, this is the input, this is the output. So we want to study input-output relations, mostly for linear systems. So the only thing I'll mention a result, and the proof is there in my notes, lecture 14. So I'm going to, it's also there in the book. So I'm just going to mention it and then move on. So we have a nonlinear memoryless system. That means the output y of t is g of x of t. Notice here, the output at the current time only depends on the current time input. And let's assume that we know x1, t2. I don't know whether we define, but we can also define cross-correlation function like this, right? So this is called the cross-correlation. We can write it xy, t1 comma t2, just as auto. If x and if both are x, we call it autocorrelation. So this we will call it the cross-correlation function. So we have two processes we correlated together. Two random variables are correlated, except this is a random variable at time t1. This is a random variable at the time t2 corresponding to y. So that is pretty clear. If it is complex, there will be a conjugation. If it is not complex, it is simply xt1 multiplied by yt2. So the question is, we want to find out this. And then we may also want to find out ryy of t1, t2, which is, of course, the autocorrelation of the output, yt1 multiplied by yt2. So remember, this is a positive definite or non-negative definite matrix. The cross-correlation is not. It doesn't have, it has other properties, but it is not as good as, it is not a non-negative definite matrix. So again, I'm not going to go into the proof of all this. So I'm going to do it a special case when x of t is Gaussian. And that's the result I'm going to mention to you. It's a Gaussian process. Utku, you remember what's a Gaussian process? Anybody?
Yeah, like all the x that we derive from different time instances are joined the Gaussian.
So how do you define a Gaussian process? So if x of t is Gaussian and I take time instance t1, t2, tn, how do you define Gaussian? You remember? So if you take any arbitrary time instance t1, t2, ti, tn, you will get n random variables. So what we mean by the process being Gaussian is that the joint density function of all this is Gaussian. That means fxs, I don't know, I think I gave it to you once. So it has this form where R is the covariance matrix of all this. So that's a matrix. This is a matrix. Then its inverse. X is this vector like this. This is X transpose, this row vector. So that's what we mean by a Gaussian process. So if X is Gaussian, anybody, is X squared, what can you say about X squared? Gaussian or not? If X is Gaussian. Anybody? Hello? We studied this. If X is a Gaussian, not a process, if X is a Gaussian random variable, what can you say? Is X squared Gaussian? Ulgar? Kublai?
No, it's not.
How about AX plus B?
Ax plus b, yes, it is.
All right, so in general, if x of t is Gaussian, what do you expect the output? Remember, this is a nonlinear function, so the output is Gaussian or not Gaussian? We just went through it.
If it is nonlinear, then it's not Gaussian.
Not Gaussian, so that's the first observation, if this is nonlinear. But my point is, you can find out, in this case, you can find out the cross-correlation function which is x of t1 multiplied by y of t2 to be proportional to rxx. This is a famous theorem. So the cross correlation is proportional to the input autocorrelation function of the, if it is Gaussian, if this is Gaussian. If it is not Gaussian, even this is not true. Of course, the output is not Gaussian, but the cross correlation is proportional to the input autocorrelation function. And this proportionality constant is, remember, we have some nonlinear function here. So let's say, as an example, let me ask you this. Suppose this nonlinear function is 4th power, some 2n. So x of t goes in, what you get as output is x to the power 2nt. So this is output. So my question to you is, anybody can tell me what is xt1 multiplied by xt2? Not xt2, yt2. So that is, according to this theorem, mu multiplied by rxx t1 comma t2, because this is Gaussian. So we are dealing with a Gaussian process. I took an even power, so that is definitely like a square or 4th power. So this is not Gaussian. And I look at the cross correlation function, it is this. So this is known as, I think, Price's theorem, P-R-I-C, Price's theorem. There are other names for it, but so mu is expected value of g prime x. What is g prime here? G is this. Hello? If gx, this is gx is, g of x is x to the power 2n. So what is g prime x? Quickly. Hello? You don't know how to take the derivative of x to the power 2n? Hello?
2nx raised to the power 2n minus 1.
Oh, expected value is only on x to the power 2n minus 1. Remember, let's say x is, maybe I should say something. It's a zero mean Gaussian process. So bottom line is, what is the expected value of x to the power 2n minus 1? And do you remember?
0.
Yeah, that is 0, right? Because it is zero mean process. So you plug it in here. So you have a new theorem. If x of t is zero mean, then if you have an even function here, the cross correlation is 0, etc. So you can deduce a lot of stuff. They are at least uncorrelated. Input and output are uncorrelated. But the main theorem is this. If x of t is Gaussian, then the cross correlation function is proportional to the autocorrelation function. So if you suspect a process to be Gaussian, you plot rxx tau and rxy tau. That you can compute. And if the results are linear, then you can conclude that the process is Gaussian. You pass it through any nonlinear system. You take any nonlinear system, find an output, compute the autocorrelation and cross correlation. And if you get a linear relationship, that tells you something about and then you change the nonlinear function, you will still get another linear relationship. It may be like this. A different linear relation, or maybe a different linear. So that will tell you that the input is Gaussian. If you want, that's a Gaussian test. So let me go to linear systems. So input is a stochastic process with autocorrelation function t1 comma t2. And I'm going to call y of t is linear. So it is L of xt. Linear means what? Anybody? If I have ax1t, a1x1t plus a2x2t, what does linear mean? If I pass it through a system, the linear combination of two inputs, what do you get there at the output? Anybody? What does linear system mean?
The output would be linear.
Yeah.
So what will be the output?
So the A1 times
A1.
the function of x1 of t plus A2 times the function, or like L of x2 of t.
So let me call L of x1 of t to be y1 and this to be y2. So everybody understands this is what we mean by linear property. Let me also define another property called the time invariant. That means if you apply the system tomorrow, in other words, if it x of t minus t naught will be what? Anybody? If y of t is the output for x of t, y of t is the output for x of t. If I delay the input by 1 day, what will be the output? Anybody? Time invariant means what?
It would be yt itself.
Not yt.
Yt minus t naught.
Yt delayed by the same amount. In other words, if you do an experiment today and you get something, and if you repeat the same experiment tomorrow, if the system is time invariant, you will get exactly the same result. Okay. So we are going to deal with systems which are linear and time invariant. Remember, most of the things we are dealing with are time invariant, at least in a short time. Otherwise, it is sort of useless to us. Most of the systems, if you switch on your phone today and you get a certain performance, you come back and switch on the phone tomorrow, you want the same volume, same quality of video, etc. Right? So time invariance is an inherent quality we need in almost all of them. Your refrigerator, your oven, whatever, washing machine, you want the washing machine to clean it the same way tomorrow also. So most of the systems are linear time invariant, at least the ones we deal with, and that's what we are going to study. So the question is, what is the, so remember, y of t, which is L of x of t, how we can write this up. So linear time invariant systems, the short notation is like this, LTI. I don't know whether you know this. So this is a result also. A linear time invariant system is completely described by its impulse response. What does it mean? So that means if you take this L system and hit it with an impulse at the input, of course you will get some function at the output. Whatever you get at the output, I'm going to call h of t. So this is the response of the input. This is the response due to the impulse at the input. So I'm going to call this the impulse response. Look at the system. Look at the input. It's a unique input, delta function. So the impulse response is completely characterized by the properties of the system. This is the system. It's an LTI system. Now let's look at y of t. So y of t is of course L of. So if you want, you can obviously write. I'll write it here. H of t is equal to L of delta t. That's what it is, right? So h of t minus t naught, because it's a linear time and response, that will be the response of delta t minus t naught. But let's look at y of the response due to some arbitrary function x of t. So an x of t, I can write it as in this manner. So this is just the definition of the impulse function, right? An impulse evaluated at tau equal to t gives me x of t. And now remember, L is linear, so this is like a summation. So the linearity goes inside here, and this is a constant. Remember, the time is only here, t is here only here. So the linearity, this is like AIs. So L of sigma AI delta function is the same as, I'll write it here. Instead of summation, I have integration or summation. Then I have AI. Then you have L of the delta function, delta t minus tau d tau. Look at here. This is h of t minus tau. I hope you can, I'm going to rewrite it in the next page. So y of t is integral x of tau h of t minus tau. So that's the first result. So if you have a system L of t whose impulse response is h of t, if you hit it with an impulse, then if you hit the same system with x of t, so this is h of t, then y of t can be written as, that's the whole point. So this is true even if it is a discrete system. All right, this you must have seen in other courses. If the system is causal, then this goes from 0 through infinity, etc. Or the input is causal, whatever. So this, anybody, what is this operation called? The one I have written. Anybody?
Convolution.
This is convolution, right? H of t convolved with this is not complex conjugation, convolution, x of t. If you are seeing this for the first time, then you need to. So this is a discrete convolution. This is convolution. And convolution has other properties. I'm not going to go over this now, right now. So what is this is where we are. We have a linear time invariant system. I have x of t as the input, y of t as the output. Input autocorrelation is rxx t1 comma t2. Let's find out rxy t1 comma t2. I want the cross correlation function. So this is by definition x of t1 multiplied by y t2 star. So those of you who are confused, look at the star coming up here, because I am assuming both could be, you could have complex input and so on. Now I am going to, so y of t is, remember, h of t minus tau 1, x of tau 1. So I am going to substitute for y of t2. So this is expected value of xt1 multiplied by integral x of alpha multiplied by h of t minus alpha, t1 minus alpha d alpha. I mean, instead of tau 2, I'm putting this, and there is a star here. So this will be star, this will be star. And let me collect all the expected value together. So this is h of t1 minus alpha multiplied by expected value of xt1 multiplied by x star alpha d alpha. So this I can write it as, look at this, this is rxx t1 comma alpha. So this integral I can write it either way. I can write it as rxx. What happened to t2? Okay, this is t2, right? t2 here, this is t2, so this should have been t2. So this is t2. rxx t1 comma alpha h of t2 minus alpha. If you call this to be some beta, and then alpha, if you call t2 minus alpha to be beta, then alpha becomes t2 minus beta. So I can also write this as Let me use that function. So Rxy t1 comma t2 is Rxx t1 comma t2 minus beta multiplied by h star of so notice this is Rxx t1 comma alpha. Instead of alpha, I'm going to put it as t2 minus beta. So this will become beta. Both the forms are fine. So h beta, d beta. So if you want, I can write this as Rxx t1 comma t2. Remember, this is a convolution, but on the second variable. So we write it like this. If you know how to read it. So the convolution is on the second variable. So that's the answer. This is the cross correlation function. Now, rather than come back later, let me also keep doing this special case. Suppose x of t is White's and stationary. Then look at here, then this will be, so let me go here. Then Rxx t1 comma t2 is actually Rxx t1 minus t2. So I'm going to substitute it here. So this will give you Rxy t1 comma t2. The question is, are these jointly White's and stationary? So let's look at it. This is Rxx. So look here, t1 minus t2. So this becomes t1 minus t2 plus beta multiplied by h star beta, d beta. So let me define a new variable t1 minus t2 to be tau. So this becomes Rxx tau plus beta multiplied by h star beta d beta. But this would have been convolution if this was minus. So this is the negative of that. So you can write this as, if you do the convolution of Rxx and h star of minus b, you will precisely get this equation. So you can write it like this. So what do you conclude here? Look at the right side. You only have a function of tau. There is no t1 and t2 separately. So you can conclude that the x and y are jointly White's and stationary, because at this point I can write this as tau because there is nothing else here. So this means x of t and y of t are jointly White's and stationary. If x of t is not White's and stationary, right? If x of t is White's and stationary, then we used it. This is only a function of tau. And then Rxy also turns out to be only a function of tau. Otherwise, we use this result. You need to understand this well, because when we do the power spectrum, etc., we will be using this. And remember, mostly the communication and signal processing part of the electrical engineering is mainly we use filtering, lot of filtering applications. And this is a filter. Your G is a filter, linear time invariant filter. So these relations become useful.
The last line is a convolution, not a multiplication, right?
Hmm?
The last line is a convolution, not a multiplication.
Yeah, you're right. So this should be a convolution right here, because this is a convolution operation. So let me summarize what we have done. Rxy t1 comma t2 is summation Rxx. What was it? T1 comma t2 minus beta h star beta d beta. But if x of t is White's and stationary, then we get Rxy or tau. I just proved it. I'm going to summarize it here. Rxx tau convolved with, not multiplication. You're right. H star of tau. H star of minus tau. There is a minus here. Why all this? You just look at the proof here. There's a minus here because this is plus So if you convolve these two functions, let's just convolve it if you are not convinced. So how do you convolve this here? So if you convolving, this will be Rxx tau minus alpha multiplied by h star of whatever it is, h star of minus alpha, because there is a minus one here, d alpha. Now you change minus alpha to beta. So you will see that this integral, the limits, if it was minus infinity to plus infinity, the limits will change it to plus infinity to minus infinity, but beta is tau minus alpha. So d alpha is minus d beta. So again, the limits will flip back and you will get Rxx tau plus beta multiplied by h beta b beta. And that's what this is. Remember, that's what we had before here. Tau plus beta, h star of beta, so that you can write it like this. So that's one property. So so the theorem is, this is what we have proved. If then x of t and y of t are jointly White's and stationary. And Rx, because Rxy tau is Rxx tau convolved with h star of minus tau. That much we have. So let's look at what is the property of the output autocorrelation function. So we want Ryy t1 comma t2. Of course, if x of t is not White's and stationary, you use this property. This is always true. The first line. And if it is White's and stationary, you apply this result. So this is by definition yt1 multiplied by yt2 star. So instead of yt1, I'm going to substitute an integral x of t1 minus, let's say, gamma multiplied by yt2 star. What am I writing? Multiplied by h, remember yt1 is, so let me write it properly. Ryy t1 comma t2 is expected value of yt1 multiplied by yt2 star. But yt1 is what? Yt1 is x of t1 convolved with h of t1, right? So this is x of t1 minus some gamma multiplied by h gamma d gamma multiplied by yt2 star. So I take the integral outside. Expected value is on x of t1 minus gamma multiplied by yt2 star multiplied by h gamma d gamma. But this is Rxy. So this is expected value of Rxy t1 minus gamma multiplied by t2, not multiply, comma t2, because this is the cross correlation multiplied by h gamma d gamma. So you can see this is the convolution on the first variable. So if you want, you can write it like this: t1 comma t2 convolved with h of t1. But we know this function itself is, we wrote it in the previous slide, right? Look at Rxy. That is Rxx t1 comma t2 convolved on the second variable. Somewhere we had it before, right? Look at here, Rxx t1 comma t2 convolved on the second variable. So this is Rxx t1 comma t2 convolved on the second variable. Another convolution on the first variable. So if you want, you can write it. I think there was a star here. This star is complex conjugate, right? Yeah, there was a star here. Okay, so what if it is Whiteson? Remember, let me consider the Whiteson stationary case. Already, if x of t is Whiteson stationary, we concluded this function is jointly Whiteson stationary. Look at the previous one. X and y are jointly Whiteson stationary. So I can write this as t1 minus gamma minus t2. So I'm going to do it here. If x of t is Whiteson stationary, this becomes Rx y t1 minus gamma minus t2. I'm going to write it like this, multiplied by h gamma d gamma. But t1 minus t2, let me call it to be tau. Then this is just a tau minus gamma multiplied by h gamma. So that's the convolution of Rxy tau and h of tau. So that's RYY. So that means RYY also is Whiteson stationary, because on the right side I only see tau. So let me do that special case next. So if x of t is Whiteson stationary, then we had Rxy tau is Rxx tau convolved with h star of minus tau. This is what we proved one line back here. I'm going to use this to conclude what is RYY tau. I already have it here. So RYY T1 comma T2, we said that it is RXY T1 minus some alpha T2 H alpha D alpha. Instead of gamma, I write alpha. It doesn't matter at this point. Now look at here. RYY is tau. In other words, RYY only depends on T1 minus T2. So I am going to put here T1 minus T2. Then I can rewrite this as I did in the previous one. T1 minus T2 minus alpha multiplied by H alpha. T1 minus T2 I'm going to call tau. So this is RXY tau minus alpha H alpha D alpha. So that becomes Rxy tau convolved with h of tau. That means the output is not a t1 comma t2. The output I can write it as ryy tau. Finally, rxy tau is here. So I can substitute the first line here if you want. So this is a very important result, this last line. So this is a system property, LTI system, and this is due to the input. So what is the moral of the story? If the input is Whiteson stationary, what can you conclude about the output? Anybody? If the input is Whiteson stationary and you pass it through a linear time invariant system, what do you get there, the output? Anyone? Hello?
Whiteson stationary again.
Yeah, that's what we have just proved, right? So we have proved that if the input is Whiteson stationary, and if you pass it through a linear time invariant system, the input and output are jointly Whiteson stationary, and the output is Whiteson stationary. That's what we have proved. So let me put this in a picture-wise form so you understand. So I don't know whether I did the mean. So the mean is what? Mean is expected value of y of t. So expected value of y of t is what? X of t minus tau multiplied by h tau d tau. So this is integral expected value of x of t minus tau multiplied by h tau d tau. But expected value of x of tau is just the mean of x of tau. So that's also a convolution operation. So you can write it as mu x of t convolved with h of t. So if the mean is not a constant, then the output mean is the input mean convolved with h of t. Of course, if the mean is a constant, if as in the Whiteson stationary case, if mean is a constant, then the output is going to be, mean is going to be that constant. This is a constant, then simply averaged over h of tau. So that's another constant. So this is c multiplied by some k. So that's another constant, c1. So the output mean also is constant. So Whiteson stationary is Whiteson stationary. So let me put all this in a picture form. So if x of t is applied to a system, the output mean is the input mean convolved with the system. That's what we just proved here. Okay, so I put that into a picture. And the autocorrelation function, if you want to remember, you can remember it like this. So to get the Rxy t1 comma t2, what did we do? I forget now. Was it h of t1 or h of t2? Anybody? First one.
h of t2.
Yeah, h of t2. Right. And then you pass it through another system, which was h of t1, not h of t2, h of t2 star. So this will be Ryy t1 comma t2. So if it is, in general, this is true. So if x of t is Whiteson stationary, we can rewrite it in a different way. If this is still true, a constant going through a system is going to produce another constant. This constant is the old constant multiplied by h of t dt. So this will be another constant, h. But the autocorrelation is interesting. So if you pass Rxx tau and convolve with h star of minus tau, you get Rxy tau. And convolve that with h of tau, you get Ryy tau. So if you remember this, it's easy to sort of remember. So Whiteson stationary at the input would mean jointly Whiteson stationary, x and y, and Whiteson stationary at the output. So what I have proved is if you apply a Whiteson stationary process as an input to a linear time invariant system, the output is also Whiteson stationary. Remember, the system is linear, so if the input is Gaussian, what do you expect the output to be? Anybody? Gaussian, right? So if the input is linear and Gaussian, the output will be not linear. If the input is Gaussian and Whiteson stationary or stationary, then what we have shown is the output will be also Gaussian and stationary. Because Whiteson stationarity is the same as Stritson stationarity for Gaussian processes. So remember, you have to put all these things together. Any questions before I show you an application? Now, these relations will come in either next class or week after next when we do the power spectrum. Any questions? Hello? Jian Chao Ma? Hello?
No question.
All right. Camila? Livia?
Yeah, no, I'm okay. This makes sense.
You understood?
Yeah.
Okay, very good. So, as I said, you cannot just ignore this because if you are in electrical engineering and if you are going to do signal processing, this is how you will use these properties to design receivers. Or for example, on your cell phone, I mean, what is the receiver? What do you pass it through? obviously you want to minimize the noise and maximize the signal. So I'll do some applications a little later after studying a little more. But let's look at an interesting problem. So I'm saying these relations, please go home and rederive this. And so here is a problem. Can you read what I wrote? Abhishek?
Yes, Professor.
No. Do you see what I have written? Do you understand at least what is the problem?
Yes.
So what the problem says is if x of t is a stationary Gaussian process, show that x of t and its derivative are independent for every t. So let's make sure you understand. If I define x of t, xt to be x of t and yt to be x prime t. Remember, these two are two random variables, right, for every t. Yes? Hello? X of t, if you fix a t naught, t to be t naught, you get a random variable. Let me call it x. X prime t naught, another random variable, x, y. So, can you tell me what type of random variables are x and y? Anyone? X is a Gaussian process. So, x small, this random variable will be what? Anybody? If x is a Gaussian process, if you fix time, what do you get this random variable to be? Gaussian. How about x prime t naught? What kind of random variable will that be? Derivative is what? Is a linear process or no? Hello?
It is linear.
All right, so y will be what? So if you take the derivative and fix time to be t naught, y will be what kind of random variable?
Gaussian as well.
It as well Gaussian. So what you are being asked is to show that x and y are independent. That's the problem. So first I want you to understand the problem. These are, of course, it is easy when I do it. But then the question is, are you able to do this type of problem? So the problem is if I do it, it has no value to you because you just look at it and nothing will register. So I don't know. Do you want to go home and try this, or do you want me to do it now so that you have instant gratification? But as I said, if I do it now, it's of no value to you. You are not going to learn anything. But if you go home and put in some effort, maybe you will appreciate. What do you want me to do? Do it now or do it later? Do it next week, or you want to try? So both are Gaussian, we argued. What we want to show is, I want to show them that they are independent. So if they are Gaussian, to show that they are independent, what is the easiest thing you could do? Anybody has any clue? To show that two Gaussian random variables are independent is the same as?
Uncorrelated?
The correlation is zero.
Yeah, showing that the correlation coefficient is 0. So what is the correlation coefficient? What is the definition for the correlation coefficient for x and y? Anybody? Is what? Hello? How do you define the correlation coefficient between x and y? You forgot that simple thing?
Xy minus mu x mu y.
Dx dy? Yeah, mu x mu.
Yeah. Mu x mu y.
Uh-huh.
By the variance of x and y.
Not variance, sigma x, sigma y.
Sigma x, sigma y.
All right, what is Ex from the problem? What is Ex and what is Ey? Anybody can conclude anything? What is Ex? What is Ey? Quickly, what is the mean of x of t? Look at the problem. Hello? Camila?
Expectation of x would be a constant mu x.
Why?
Because it is a stationary Gaussian.
Okay, so what will be, that's a constant, but the constant is not given, right?
Yeah.
So what about expected value of y? Y is what? This is where you have to use this. That's what I'm saying. You need to go home and think. Look at this picture.
Is it 0?
Look at the picture, the top picture. What is h of t here? Anybody? What are we doing to x of t? Hello? What is the system here? You're taking the x of t and y of t is what? Look at the problem. Y of t is x prime t, right? So what is the system here? Anyone?
We take derivative, so we will take derivative of mu x, which will be 0.
All right, so you conclude that, so these are the things you need to go home and let me not, so this is 0. And so if you want to show, see whether rho is 0, that's what being asked. All you need to worry about is this. So what I'm going to ask you is, can you show that, remember it's a Whiteson stationary process x of t. So already you can use this. So I'm going to ask you to, it's already stationary. So Rxy, see whether you can prove this. Nothing else is given. X is, you can see stationary or Whiteson stationary, Strickson stationary, whatever. Do you want me to do it, or do you want to try a little bit at home? Anyone? Okay, to give me some clue, what do you want me to do? Jianliang Feng? Feng.
Yep.
Did you understand the problem?
Yep.
So tell me, what do you want me to do? Do it here, or do you want to try?
I will do it at home.
All right, so if that is the case, let me not completely solve it. I'll give you I'll give you 1 week, and next week somebody, if you cannot do it, just to remind me, I'll go over the proof here. But you have to make use of this property here.
Okay.
So let me give you a little bit clue. So remember, x is Whiteson stationary, so you have Rxx tau. Then it seems, so if you from here, this is the system, right? This is your linear time invariant system, taking the derivative. So that's x prime t. So if you look at this Rxx t1 comma t2, This will be dt by d, what did you say, dt2, right? So this is derivative with respect to t2 rxx t1 comma t2. Then you take the derivative with respect to t1 to get, so this output would be double derivative dt1 dt2. But you have to, for this problem, you have to work with here. So this is r x prime x prime. In general, t1 comma t2. If x of t is not Whiteson stationary, then this is true. If it is Whiteson stationary, I want you to go home and start putting this as t1 minus t2, simplify and see, etc. I mean, then you will be able to prove that that correlation is zero, and hence they are independent, etc. So, I can do it now, but as I said, if I do it, then you don't have any value. So let me leave it here for you to think about it a little bit. So as an application, suppose we have an input process whose autocorrelation function is like this. So you have an input process W of t whose autocorrelation function is RWW T1 comma T2 is some constant multiplied by delta T1 minus T2. So what's the, if T1 is not equal to T2, what is the value of this autocorrelation function? Anybody? If T1 is not equal to T2?
0.
0. And let's assume the process is 0 mean. So that means the process is such that even if T2 is slightly beyond T1 or before T1, the two random variables are uncorrelated. In other words, so this is something like this, that if you take two time instants, however close it is, they are uncorrelated, the random variables. So that means it's a crazy process which has no relation to what is going to happen next or before. So we call this, I'll explain to you the reason in a couple of weeks, we call this white noise. You know, it's obviously a noise which with no sensible information content. And it's called white noise for a reason. So if this is the input, look at the output. The output will be y of t, will be, of course, x of t convolved with, not x of t, w of t convolved with h of t. So if you go through this, we remember this is already Whiteson stationary. So the rxy tau will be what? Rxx tau q multiplied by delta tau convolved with h star of minus tau. So that's simply q of h star of minus tau, and ryy tau, because it is this is Whiteson stationary, q of w of tau. This will be this convolved with h of tau. So this will be q multiplied by h star of minus tau convolved with h of tau. So bottom line is that's also Whiteson stationary. But so the understanding, what I want you to understand is the output autocorrelation actually only depends on the system properties. Look at here, only the system properties. And so this has got implications. So if you want to, if this is a black box, if you want to study about a linear system, but it is a black box, you can excite it with the white noise and look at the autocorrelation function of the output. See, from there you can find out the system poles and zeros, etc. And this becomes a little more clear when we have when we study the corresponding power spectrum. So this is just an application already of that. Any questions? So let me quickly, all this is true for discrete time systems also. That means the time is discrete. And I'll come to this specific example soon. And the input also is defined only for specific values, could be multiples of, so this means you have a process, but the process is sampled at t equal to nt. That's one way to generate a discrete time process. But a discrete time process is passed through a discrete time system to generate y of n. So that's the discrete time convolution of xn and hn. So that is sigma k xn minus k multiplied by hk. So you can see that rx x n1 comma n2. So generally, let me write it like this: rxx n1 comma n2, discrete time values, right? T1, T2 is n1 and n2, or n and m. So the cross correlation function rxy n comma m is expected value of xn multiplied by y star m. But this you can write it as expected value of exactly the same result, summation. So for ym, I am going to copy from here, x of m minus k multiplied by hk. So star here, star here. So this is summation is on k, expected value of xn multiplied by x star of m minus k multiplied by hk. But this is rxx n comma m minus k. So rxx n comma m convolved it on h of m with a star here. So you get the same result. If this is Whiteson stationary, notice this will become n minus m plus k. So if x of t is Whiteson stationary, x of n is Whiteson stationary, then rxy n comma m becomes summation. You can look at your expression rxx n minus m plus k h star of k. And if so, this becomes only a convolution of using this. So if I define n minus m to be some new variable L, this becomes R of L convolved with H star of minus L, because L plus K. So R xy L is RL convolved with H of minus L, or RxY N is RxX convolved of N convolved with H star of whatever is the variable. So that's also what you call jointly Whiteson stationary. Finally, RYY n comma m is expected value of yn y star m. But for yn, I am going to substitute xn minus, let's say, j. Then you have xj y star m. Expected value here. So this is summation j. Expected value is on xy, right? X of n minus j y star m hj. But this is rxy n minus j comma m hj with a summation. So that's the convolution of rxy. Remember, n minus m on the first variable. So n comma m convolved with hn as before. Now, if this is Whiteson stationary, then this will become n minus m minus j. N minus m is a new variable, L. So you get, so we had before rxy L is rxx L convolved with H star of minus L. So if the If the cross correlation is Whiteson stationary, then this will become, where is it? Yeah, this will become here, n minus m minus j. N minus m is L. So RYY n comma m becomes summation RXY n minus m minus L or j there, j. But n minus m is, I'm going to call L. So this is L minus j. That's just the convolution of RXYL convolved with HL. But RXYL is here, RXXL convolved with H star of minus L convolved with H of L. And if you do, so that means RYY also is a function of L only. If you don't like L, you can put it back to N or M. So you get RYY, just replace L by N, RXXN convolved with H star of minus N convolved with H of N. Again, this is a system property, this is an input property. So what is the moral of the story? Whiteson stationary at the input means they are jointly Whiteson stationary. Because Whiteson stationary here gives you jointly Whiteson stationary. And if it is jointly Whiteson stationary, this is here. If it is jointly Whiteson stationary, then the whole thing is Whiteson stationary. So this becomes RYYL. Is also Whiteson stationary. So you get Whiteson stationary. So Whiteson stationary at the input means Whiteson stationary at the output, and this is the relation. And we will use these relations. I'm not going to rederive it again. When we discuss the power spectrum of input-output relation, I will use these relations. So please go home and review this and make sure you are sort of good with this. And so the mean is, I forgot to tell you about the mean, but the mean is, you go through the same thing. RY mean is the summation of Rx mean convolved with the system. So if the input is stationary, then the output is also stationary. So this is so what is the story? Whether discrete time systems or continuous time systems, if the system is a linear time invariant system and the input is Whiteson stationary, then input and output are jointly Whiteson stationary, and the output is Whiteson stationary. Of course, if the input also happens to be Gaussian, then all stationarity is same as Stickson stationarity, because input is Gaussian means output is Gaussian. Input is Whiteson stationary means output is input is Stickson stationary, and hence output is also Stickson stationary. Something I forgot to show you is that I'm going to leave it to you to look at the book for a proof. If the system is linear and time invariant, and if the input is Stickson stationary, not necessarily Gaussian, Stickson stationary, then the output is also Stickson stationary. So the way the proof goes is, remember here you have, if you take a set of random variables x1, etc., xn, at time instance t1, t2, etc., tn, and if you shift the time instance by t1 plus c, t2 plus c, etc., tn plus c, you want to show, by Stickson stationarity, we showed you last time, these two are the same. So you want to prove the output also, you want to find out the joint density function at time instance t1 to tn, and you want to find the joint density function at time instance t1 plus c, t2 plus c, etc., tn plus c, and make use of this relation. So essentially, remember, go back to that one variable. So y and x are, y is g of, or whatever, L of, call it g of x of t, L of x of t. I mean, it will be like integral. It's a linear operation, right? So it's like summation x of ti multiplied by h of ti plus delta, etc. Right? So that's a linear operation. So you can the transformation is there's a Jacobian. So this will come out to be 1 over the Jacobian of density function evaluated at x1 xn. But x1 through xn is key is here at time instance t1 through tn. And similarly here also you'll get an operation 1 over j, the density function evaluated at t1 plus c, etc., tn plus c. But you see, these two density functions are equal. So similarly, from that argument, you can argue that these two density functions are also equal. That means the joint density function of y of t is y strict and stationary. That's how you prove it. And just review this proof also. So this is true whether it is Gaussian or not. Of course, if it is Gaussian, you don't need a strict and stationarity. White sensation. Any process which is strict and stationary will generate some other process. Nothing to do with Gaussian, but the strict and stationarity will be preserved. Let me continue with the discrete time systems, because when you do modeling, etc., or with the measurements, usually this is what we will end up with. Even for continuous time systems, we sample the system at many points. So there is, so I want to study a special discrete time system called ARMA system, ARMA processes. And we'll connect it with systems also. So look, some input to discrete time system, some output to discrete time system. All right, so let's look at this relation. What am I writing? Obviously everything is linear relation. So look at this. The current output depends on previous p values, earlier values, and it depends on the q earlier values of the input. Own values. See, this is xn values. This is like a regression, because the current value depends on yesterday's value, day before yesterday's value, p yesterday's values, and it also depends on the input values and its previous values. So this is called regressing on itself. So that's why it is called so this part is called auto regression. And this is like a moving average. If you put all the b's equal to equal, then this is like the average. So if this is today's temperature, this is just taking the last q days temperature, q plus 1 days, and averaging it, right? If all the b's are equal to 1 over q plus 1. So that's like a moving average. So that's why we call it ARMA process. So the xn is called an ARMA process. And a lot of things that we study can be put it into this, and it's only a question of which variables and what is the value of p and what is the value of q. So this is called an ARMA PQ process, because P is the regression value, Q is the moving average value. So you remember, you have a lot of flexibilities. You have the flexibility with the coefficients, you have the flexibility with the P and Q. So you may say, why this? As I said, a lot of things you can fit it into this model. So the simplest model is this one. I take P equal to 1, Q equal to 0. So the x of n will be minus A1 x n minus 1 plus B naught Wn. So that this is called AR1, right? Because Q is 0. So it depends on the previous value of the output and the current input. So this is the simplest one. If it is AR11, you have one more term here, etc. So we'll study all this generally. So let me write it. It is a little easier. Why this minus sign, you will see. It just makes it easier. So K equal to, also this summation I'm going to use using a summation sign like this. And this one I can write it as BKW n minus K. K goes, these two are different summations. So one is P, one is Q. This is an ARMA PQ. So to give it a system flavor, remember I didn't tell you what this system is. To give it a system flavor, let me take the Z transforms on both the sides, if you know. So the Z transform is xn Z to the power n, summation on n. I'm going to call it Z, x of Z, capital X of Z. So here this will be, if you, anybody remembers what is the Z transform of a delayed signal? Anyone? What is the Z transform of this sequence, xn minus k? Anyone? So you substitute, you go through this definition, substitute xn, you can do it here. Xn minus k multiplied by zn, you need to, so I'm going to replace n minus k by I, so this becomes x of I, and remember then n becomes k plus I, right? C to the power k plus I. Summation is on I, so zk goes outside, so this is zk, but whatever is remain is x of z. So this is, so that's what I've written here, x of z multiplied by this. Similarly here, bk zk multiplied by w of z. This is x of z. So there's a minus sign here. Let me collect all the x of z terms together. So I get 1 plus sigma ak zk, k equal to, k goes from 1 through p, and here k goes from 0 through q. Multiplied by x of z is sigma bk zk w of z. So you see, I can write the output as something bk zk divided by 1. So because of this plus sign, I put this minus here. If you don't put the minus, this will become minus, that's all. So those of you who know a little bit system, you can see this is the transfer function, and this is the input, and this is the output. So the output transform is the input transform multiplied by the transfer function. So this system, ARMA PQ system, is this transfer function. So I'm going to call this H of Z. So in ARMA PQ system, which is, if you want to represent it this way, let's see what this system is. So xn is, of course, minus sigma ak x of n minus k, k from 1 through p, plus sigma bkw n minus k, k from 0 through q. Then h of z, the system here. So Hn, which is a transform of h of z. H of z is here, so I'm just going to write it down. B0 plus B1z plus etc. BQZQ divided by 1 plus A1z plus etc. APZ. So this is the transfer function. Of course, this is, you are very familiar. This is just a polynomial over polynomial, right? So moral of the story is, if you have an ARMA system, the transfer function is the ratio of two polynomials. So those of you who remember, I can replace this as the denominator. Of course, I can write it as the product of roots. Then I can go through partial fraction. There will be p polynomials, and so this is your h of z. And if you do inverse transform on each one of this, you can get the impulse response. So that will turn out to be something like zk to the power n. And if the system is stable, all the ck's are less than 1. I just went a little quickly. But you see, this you know, right? If you have any polynomial over polynomial, you can write it using partial fractions. I'm going to assume q is less than or equal to p. So you can write it as a constant divided by these roots. The denominator has p roots. I call them z1, z2, etc., zp. Then if you take a term like this, if you take a function whose impulse response is, remember, if you take a function whose impulse response is an, then the system corresponding to that is sigma hn an, right? Hn zn, but hn is an zn. Let's say n equal to n greater than 0, n equal to 0 through infinity. Then this is simply za to the power n, 0 through. So this is 1 over 1 minus ca. Its root is at z equal to 1 over a. So which is what I'm doing here. So you can see, you can rewrite it in this fashion. Whenever you have an impulse response like this, you can rewrite it like this, or you can rewrite it as, you pull out a outside. So this becomes 1 over a, 1 over z minus 1 over a. Either way you can write it, right? Either, or you can write it as 1 minus czk. So what is this? So if you add many, so if you add different impulse responses like this, you will get an ARMA system. So an ARMA system, remember, stock markets use last 50-day moving average. So that is where P is 0 and you're only using the, I'm sorry, Q is 0 and you're just using the previous values of the data. So h of z, which is the ratio of two polynomials, b0 plus b1z. A lot of these things have nothing to do with this course, but we need all this stuff, which is a1z, etc., apzp. So these are the system parameters. If you want, you can write this in terms of the q zeros and the p poles, right? Z minus z1, z minus z2, etc., z minus zp. And here z minus alpha 1, z minus alpha 2, etc., z minus alpha q. So these are the zeros, these are the poles. So an ARMA PQ system has p poles and q zeros. So those locations will tell you the properties of the system, etc. So remember, the autocorrelation function of the output is, you can write it in terms of, you know, the impulse response, which I gave it to you here. So it's a linear time invariant system. You know the impulse response. Then the impulse response convolved with the input autocorrelation twice will give you the output autocorrelation function, if you want to go that way. But this is, I have done this in great detail in my lecture 14, so you should see this, but now it should be easy for you to read. Now that, so if Hn is sigma ak sum zk and k equal to 1 through p, then your input or output, you can also write it as Hn convolved with input if you want. So all the poles and zeros, everything is captured by this input. So this is the impulse response. But if you don't want to write it this way, you can write it the original way in terms of the autoregressive part and the moving average part. And in particular, usually people, so if you want to study the simplest system, you put Q equal to 0 and P equal to 1, you will get a single pole model. That's called an AR of model 1. If you put 2 poles, you get AR of model 2. There are thousands of papers on this topic. This is a very well studied and extremely useful topic, so you should know a little bit more. And so what I'm trying to say is this is an application. I'm just trying to expose you to new ideas and how people look at this and so on. So there is a AR1 and AR2 in great detail I have written in notes, so I'm not going to repeat everything here. But I do want to do one more item before we finish this class. Any questions? So remember, we have P regressions, and we also use some moving average from the input process. This is the way, so you can either define the output through this A case and B case, which are the coefficients of the system, or you can define it this way. But the impulse response is completely defined from this function. But it takes some work to find out the impulse response. Then you can directly convolve this, but this is not giving you any physical intuition. This is giving you what is going on. So you put different values of P. So which model will fit your data? That's the whole, so data fitting. So you collect some data, you can always fit in some ARMA PQ. That's the theorem. I mean, there's also a book by me on system identification. It mainly deals with how to fit a ARMA PQ. Now we can bring in, I'm not going to bring it here, but you can also bring in, I want the system to be stable. If you know the concept of stability, I also want the system to be stable. So the question is, given some data, I mean, at least you are open to problems now. Because if you have a system, you want it to be stable. If you don't know what is stable, that's a difference. So these are the type of things I've addressed in my book. But here, at least you appreciate, if you give data, how do you find a best? So you have to see what do you mean by best fit and so on. So can I fit is an AR1 process enough? An AR2 process enough? What is the best value of P? Is it P equal to 10, Q equal to what, etc., etc. So you collect some data. The whole point is almost all data can be fitted by some ARMA process, but the question is, can you also make it stable, the system? So that is some sort of well-behaved process. None of this we are going to answer in this class, but you can begin to see how this course is opening up to new problems. But let me do a little more. Let me show you some, because of the, you can see there is a lot of structure in the data. What do I mean by is, look at this on the top line. It's a it at least it's not crazy. It depends on the previous n values, p values, and it depends on some input process. You can think of this as some sort of noise process if you want. So it has got some structure, and how do we capture? So one assumption we actually make is the input noise. Anybody, what does this mean? The last line, what does it mean physically? Anyone? About the input, what does it say? Hello? What does this say about the input? So the input, the current value and the past values all, and let's assume it to be zero mean.
Independent.
They are uncorrelated.
Uncorrelated. That's a reasonable assumption, especially if it is noise and so on. If it is so, if you say whatever you are seeing in the stock market, let's say you say I want to model it by an ARMA, at least for a short duration, an ARMA model. The question is, what is the best fit? Or some other data that you collected, some behavior, some social whatever, or heartbeat or something. I want to. So the question is, I don't even know what is the P and Q, but I am going to assume that I want to assume that the input to be it is driving. Remember, this is the input. Input has got this property. This is the driver, right? W of n. So Wn of n. So if W of n, if this is uncorrelated with this previous past, that's a reasonable assumption. And another assumption is that was the second assumption is W current value of the input. What does this mean? Anybody? What does this mean? The second one. Hello? So this is the present, past. What does this mean? Anyone?
Input is uncorrelated with past outputs.
Not output, past inputs, right? I'm sorry, the input is, the current input is not going to influence the past values of xn because, right? Because look at here, xn only depends on the past values of w, right? So some noise that is going to happen tomorrow is not going to influence today's output. That's what it says. If this is today's output, this is tomorrow, right? N minus k is in the past. The past is not going to be influenced by today. Yes or no? That's clear, right? Hello? See, yesterday's stock market value wasn't influenced by today's whatever is this noise. You think of this election as noise, whatever, right? So yesterday's stock market value, or 1 week back, it was certainly not decided by what was happening today. So that's the assumption. So with this, let me quickly generate the output autocorrelation function, expected value of, I'm going to assume, I think the stationarity is clear, right? Because I can write, look at here, because I can write the system like this, if the input is Whiteson stationary, you can see the output is Whiteson stationary because it's because of this relation. So let me I'm going to assume that the input is Whiteson stationary. Consequently, the output is Whiteson stationary. So I am calling T1 minus T2. That's Ri. That's the reason I am writing it like this. So now I'm going to substitute for, after this we will stop. So this is all there in my notes. This is Ai x of n minus I and ak, right? Ak, I'm going to use a different symbol, k xn minus k multiplied by x star of n minus I. Plus summation. Remember, I am substituting for x of n. X of n I am substituting. So this is going to be bk w of n minus k and x star of n minus I. And there is an expected value on both. So expected value is, just to save, this expected value comes and sits here. And the same expected value comes and sits here. So, but this expected value is T1 minus T2. So let me write it as, so this is going to be summation AK T1 minus T2. So this is I minus K. Summation is on K. K is from 1 through P, right? And plus summation here, BK, expected value of W n minus K and x star of n minus I. Remember, K goes at the most from 0 through Q. So K goes, so if I is, remember, K goes at the most from 0 through Q. So if I is beyond Q, you can see that this, using this property, if I is beyond Q using these two properties, the past is not influenced by the present value and this value will be 0. So this is a key ARMA relation. So let me write it down in the next page. So the output autocorrelation has this property. So basically what it says is if you look at the large values of Ri, it only depends on previous p values of Ri. The output autocorrelations have some linear dependency. And using this, if I define a matrix, so this is true for, so basically if you take I to be large, Ri depends on the previous p values, right? K equal to 1 through p. So there is a linear relation between the Ri's. So if you can see that, let me define a matrix like this and we can leave it at that if you want. So you can see, you can go on like this.
Can you move the paper up a bit?
Oh, yeah. So I'm just creating an arbitrary matrix and you will see why I am doing this. So let me use the previous relation. Look at here. If this K is very large, then think of this K as I. Then this one depends on the linear combination of this. This one depends on the same linear combination of previous P values. So if I generate a big enough matrix, there will be linearly dependent columns and hence its rank will be 0, right? So we could say that if this k is beyond p, then this relation rp plus 1 will depend on the previous value. So these are all dependent. And so the big property is the determinant of dk is 0 if k is beyond p or k is large. So there are infinite conditions, and that's a property of ARMA systems. So you can see, you can go on and on like this. You can see starting with something simple, how far I have come up with. So this is a famous property. Matrices like this are called Hankel matrices, because if you look at all these diagonal entries are equal in this manner. So this is called a Hankel matrix. And this property, I think, is due to Kronecker. Kronecker was a mathematician from last century or before that, I think. So you can use these properties to, remember, usually the problem is you have data. How do I go back and find the system parameters? You can use these rank properties to find out about the A case and B. So you can see already this will give you a clue about P. You start checking this as a hypothesis testing problem. So at some point you are going to get a rank to be 0 beyond all values of P, and that will give you P. And autocorrelations, you estimate them and find out, etc. So the data, of course, you want the data to tell you what is the best value of P. I don't want you to guess the data saying, let me try to force an ARMA 1 system into. So you compute the autocorrelations. Their rank of a structure will give you, so you can see here, the rank will be P beyond when K is greater than, determinant will be 0 when the size is greater than P. And that, so if you come by smaller sizes, you can see that suddenly the determinant goes to 0 and you can identify P. Then you can use these equations. Once you know P, you can use these equations to compute the AI. So suddenly you have all the denominator parameters. And then you have to use them to, we missed a few equations there. You can use the previous equations. Remember, some of these equations will be non-zero. You can use them to compute the BIs and so on. So that's how we go in.